As we described earlier, strong acids are acids that are capable of dissociating 100%, meaning they have acid dissociation constants greater than 1. In fact, they're much greater than 1. Likewise, strong bases dissociate 100%, and they too have equilibrium constants which are far greater than 1. However, rather than talking about Ka, which stands for the equilibrium constant of an acid, we have Kb, which is the equilibrium constant of a base. With strong acids and bases, though, when we write the reaction, we only write our normal reaction arrow pointing to the right. When we have weak acids and bases, we use the equilibrium arrow to represent the fact that they are indeed weak. It helps us indicate that we identify and acknowledge that these are weak materials. So when we have an acid, anytime we have an acid and an equilibrium constant, we describe it as being Ka. And one thing we can do to identify a reaction has a Ka value is, is identify that all Ka reactions have the hydronium ion in them. So if you see an H3O+, we're talking about a reaction with Ka. Any reaction that has hydroxide, we talk about the Kb value, the equilibrium constant for the weak base. And one thing we can see that, or look up when we're working with weak acids and weak bases, are tables of equilibrium constants. Every single weak material has a Ka value, and likewise the conjugate base has a Kb value. So if you find Ka, you can either calculate Kb, as we'll talk about in a few minutes, or you may find that that value is already in your table. So you can see hydrofluoric acid, the top acid there, has a Ka of 7.1 times 10 to the minus 4th, which means the fluoride ion has a Kb value of 1.4 times 10 to the minus 11th. And the relative, I don't want to say strength, but how good an acid is dependent upon the magnitude of Ka. So Ka values closer to 1 are better acids than Ka values far away from 1. So for example, benzoic acid is an acid, but it's not as good of an acid as, for example, aspirin or acetosalic acid. So the closer these values get to 1, the better the acid or the more acidic it behaves. So for every weak acid and weak base, there's a conjugate ion. And these conjugates have acid dissociation constants or base dissociation constant, which is based off of the weak material. So the conjugate base of a strong acid has no measurable strength. So something like hydrochloric acid, the conjugate ion is chloride, and because hydrochloric acid is strong, that means the chloride ion is negligible. So ions from strong acids make negligible bases, and strong bases have ions which are negligible acids. In terms of strength, or the strongest acid that can exist in solution, we have the hydronium ion. There is not an acid more acidic than H3O+. Likewise, for a base, you can't have a stronger ion than hydroxide. So, talking about these acid-base pairs, let's talk about the effect of sodium chloride versus sodium fluoride. Well, sodium chloride produces sodium ions and chloride ions in water. And when these ions are floating around, they could potentially react with water to produce NaOH and H+. The problem with this is sodium hydroxide is a strong base. And since it's producing a strong base, it would immediately dissociate back into the reactants, meaning no reaction occurs here. Chloride ion could react with water to produce hydrochloric acid and leave behind hydroxide. Well, again, hydrochloric acid is a strong acid, meaning that there's no reaction here. So anytime you have a conjugate ion that reacts with water, then if it produces a strong acid or base, that reaction will not take place. So it has no effect on the pH of solution. Fluoride, on the other hand, fluoride is capable of reacting with water to produce hydrofluoric acid and hydroxide ion. This reaction does occur because HF is weak. As long as you're not producing a strong material, then the ion is capable of affecting the pH of a solution. So what's the net effect of a fluoride ion? Well, it creates OH. OH relates to base. So adding fluoride ions makes a solution more basic. So let's talk about this in terms of equilibrium constants. So we have Ka and Kb. And for a generic weak acid, HA dissociates into H plus and A minus. And if we take the conjugate ion of that acid, that is A minus, and react it with H2O, we get OH and HA, and this is a Kb reaction. Well, remember from manipulating equilibrium expressions from the previous chapter, we could combine these two equations and get the anions to cancel. And what we're left with after canceling out the weak acid as well is the dissociation of water, H2O into H plus and OH minus, which we define as Kw. So Ka times Kb equals Kw. So for any weak acid with a Ka value, you can calculate Kb. Just remember, Kw is 1 times 10 to the minus 14th. So here's a number of weak acids and strong acids, and we see the strong acids have a large Ka, or we just say strong acid, and it has no Kb value. For things that are weak, we can see we have both Ka and Kb, and if you want, you can multiply a particular weak acid times its conjugate base, and you will find that those Kw values is equal to Kw. So if you know one, you can determine the other.